Hi everybody, back to our basic electronics again for series 3. Last time I mentioned about our inductor, capacitors, and some application of the capacitor circuit and inductor circuit. For this one, I'm going to talk about what I left off, from the last time, and we get into reactant of capacitors and inductors. For capacitor, as I mentioned to you before, we can write the voltage in the term of the real part of Vn exponential of j omega t, and also Ic simply equal to c dvc by dt. And let's start with the input become v0 cosine omega t, and then you differentiate dvc over dt, or the voltage across capacitor, and you end up with the real part of v0 exponential j omega t, and simply divide by xc, and this become xc, and we call is as the impedance of capacitance. Thus become frequency dependent in the term of omega, and omega equal to 2 pi f. For example, we have a capacitor to be 1 microfarad, and at the frequency 60 hertz, you end up just like substitute or plug in the number here, xc equal to negative ji over omega c, and then you can see the different frequency. The higher frequency, the lower impedance, and for the special case DC, and we know that the frequency become 0 and your xc become infinity. So when you connect capacitor to DC supply, you're going to have become just like open circuit here. So it's just like blocking the DC supply. And as I mentioned again, you can see the impedance or of the capacitor, or the reactance of capacitor, is become a negative number of complex number. But for inductor, you're going to have the impedance become positive number of a complex number. So it's worked out very nice. This one become negative, and this for inductor it's become positive. And you can notice again that for higher frequency, you have lower impedance, but for inductor, for higher frequency, you're going to have higher impedance, and that's why we use that for different purpose when you design filter circuit, the way you connect capacitor and the way you connect inductor. You can just guess, or you can tell that if you want the high pass filter, how you're going to connect C and L, and the same thing if you want to like low pass filter, you know how to connect the capacitor and inductor. What I meant is that for, let's see, this is your output. You know exactly that your output is going to be depend on the impedance of capacitor. So for higher frequency here, you know that your capacitor going to be the impedance of capacitor going to be like smaller and smaller. So when you're thinking about a voltage divider, and this gives you a smaller output signal, correct? So it simply is going to become the low pass filter. That means you get rid of the output voltage when you have higher frequency. Same thing as the inductor. You know, when you connect the inductor as the output, and you have your V out direct proportional to frequency, because you have like omega here is 2 pi f. So the higher the frequency, you're going to have the higher V out. So for smaller frequency, you don't have high level of output voltage. So this one is become a high pass filter. Okay. Take a look at another circuit here. You have capacitor connect to the supply voltage, and you know that Vt equal to A cosine omega t, and A simply become 110 volt RMS, and you want amplitude, you just multiply square root 2 to 110, and then you end up with 156 volt. And now for the current, if you take a look in the simple form here, you simply divide the voltage by the impedance, and then you end up with J omega C multiplied by the amplitude of the applied voltage, and your I0 become 0.059 because you have capacitor become 1 microfarad and the frequency is 60 hertz. Okay, you just plug in the number right here, and your A is the 156 volt. Or you just simply you don't care about a complex number, you want to find only the amplitude here. You just multiply omega by C and by V. When omega is 2 pi f and f equal to 60 hertz, C is 1 microfarad, and the voltage is 156 volt, and you end up with 0.059 amps, or equal to 59 milliamps. Now take a look at the power in reactive circuits, or when you have capacitor and inductor connected to the circuit. For the reactive circuit, your voltage not really proportional to 1 over I, so your power is not equal to I multiplied by V. Why I say something like this? Okay, well, you take a look at the plot between the current and the voltage here. When you're talking about a P equal to IV, it's simply take a look at the plot of V here. It just calculate for the area under the curve, and for the AC signal, especially for the sinusoidal signal, you can find the area under the curve for one period. You can see that this one is a positive area, and this one is negative area. When you add them up, this gives you 0 for one period. So that's why you cannot calculate by this equation. And I also say that the power equal to IV is not applied for a reactive circuit, and you also be able to write for the power. You can calculate for one period, 1 over T, when T is the period. You integrate from 0 to 1 period of Vt input signal multiplied by It, then dt. And for the power also, you can write in the term of the real part of the V cap multiplied by complex conjugate of the I cap. Or you can switch around. You can either V cap conjugate multiplied by I cap. Okay, and this one I mentioned about the complex conjugate. You simply change the sign to be opposite of whatever you have, at the beginning, at the start. For example, you have the voltage to be 1 volt. Your I current equal to V over negative j omega z. And then for if you want to calculate the power here, you can see that's why it gives you 0. Okay, you pick up this equation here, so the power becomes the real part of the voltage multiplied by the complex number of the current. So your voltage is 1, and I complex conjugate become negative j omega z, and you want to pick up the real part, and it has no real part, so this one gives you 0. Or you can switch around and V complex conjugate, but V is the real part, so you don't have the complex conjugate over there, and I still become j omega z. You pick up this one, so you don't have any real part of your power. It still give you 0. Alright, that's just for example. Now let's take a look at the circuit when you connect, when see your capacitor in series with resistor, and you have the input become V0 cosine omega t, and when you find the total impedance of the whole circuit here, it just become R minus j omega z. This is the impedance of capacitor, and V cap become V0, and you can find the current flowing through the circuit equal to V0 over Z total. So you simply divide V0 by R minus J over omega Z, and you rearrange the term here. You're going to end up with the power become the V input square multiplied by R over R square plus 1 over omega C square. Okay, this is the power dissipation, to the resistor here. And if you consider another term like V cap, the amplitude of the V cap multiplied by I cap, what I want to point out is that you're going to have another parameter that's very important also, that we call the power factor here. Okay, let's take a look at how you come up with the power factor. The power factor simply become the ratio of the power that you calculate, from here, when you have like it seemed to be your power across R here. It's just like the output, and divide by the magnitude of the V cap multiplied by the magnitude of I cap. So you start by V, you just put V0 here, and your current, it just become this term. Again, how do you get the current? Well, you pick up, from above here that you already calculate. I never change. And this one you are just like rearrange the term. That's why I have you cancel this one out. So this one still have the power of 1 over 2, or square root of R square plus 1 over omega Z square. That's why I have the term look like this one, and you multiply them together, you end up with the V0 square, and this one still have like the cancel out 1 over 2, so you have 1 over 2 left here, right? And when you find the ratio between this power and this power, you end up with the R over R square plus 1 omega C square and 1 over square. This is we call the power factor. Okay. Just tell you how much the power get into your output or transfer to your output. And if you consider about the power factor is going to be in the range of 0 and less than or equal to 1. Okay, you can take a look at this. When let's see here, if for here, take a look at the power factor here. We're talking the power factor is going to be in the range of from 0 to less than 1. You just take a look at the frequency here. If for very small frequency, you can go to 0 to infinity here, and very large number of frequency. For a very high frequency, you can see that this term drop, right, because they have even or square. You divide 1 by infinity, so this one drop. So you end up with the r divided by r, because this one have 1 over 2 or square root r squared. And for infinity, you're going to have the power factor to be 1. And for the very low frequency or even a DC circuit, what is your frequency? Your frequency is becomes 0. When you have f becomes 0, what happened? This term is very large, right? Because you divide by 1 over something close to 0 or the very small number, and you end up with this term is very large. So you divide something by a very large number, that gives you 0. So this is the period reactive. Okay. Actually, I should switch around period resistive. It should be give you this one 0. Or if you don't have this term here, I'm sorry, that's for period reactive. Let's take a look at a simple term first, period resistive. So you don't have this one, alright? So it gives you 1. And when you have period reactive, this term is very large, and you divide something by the large number, it gives you 0. Okay, just give you the idea about what happened to the power factor here. Take a look at another circuit. You have C also C in series is R. What I want to point out is that simply all the power will transfer to the resistor here. The resistor is at the output. Okay, let's start with the P equal to real part of V cap multiplied by a complex number of the current. And you know I equal to V over Z, and become amplitude of your input signal here is V0, and you divide by total impedance. So it's become R plus 1 over J omega Z. And then you rearrange the term, you end up with the I cap become this one, and then you pick up I complex number here. So you just simply change the sign here from negative to be a positive. And then you calculate for P, become the real part of V multiplied by V0 multiplied by R plus 1 over J omega Z divided by R squared plus 1 over omega C squared. And you end up with the P equal to V0 square R over R squared plus 1 over omega C squared. And now you take a look at the power to resistor, because resistor is at the output. You can do the same thing. The power, transfer to R is simply become a V square over R. and your VR simply voltage divider here. So you pick up the amplitude of input voltage, V0 multiplied by R over R total, so R plus 1 over J omega Z, and you do the same thing, you rearrange the term, and this one you have the negative side here. And then your power simply become, because the power is become already the real number only, so you simply look at this as the VR cap multiplied by VR cap conjugate and then divide by R. This is your VR cap, and this is your VR cap conjugate. Just simply change this negative side here to be positive side here, and then you divide the whole thing by R, and you end up with the PR equal to V0R multiplied by R squared. And you take a look at this one here. You rearrange the term. Just use the simple math. You will see that two terms are equal, and that's why I say that all the power transfer to a resistor. Okay, this one the power to the resistor. I'm sorry, this is the file I got is the power to resistor to be I dropped this down, V square, sorry about it, because this one multiplied by this one becomes V0 square. So it's exactly the same, alright? You can repeat the calculation by yourself. If I have C equal to 1 microfarad, R equal to 1.0 k ohms, and V0 equal to 110 volt VRMS, and frequency equal to 60 Hz, I can calculate the P average. Just to be this term here, I just plug in the number. V0 become 110 multiplied by 2, because 110 is VRMS. R is 1k, so 10 to the cube ohms. Divide by R square, divide by 1 omega Z, or when omega is 2 pi f, if the frequency is 60 Hz, and your C is 1 microfarad, so you have like 10 to the negative 6 farad. Now another application of capacitor and inductors that we use in our audio and so many filter circuits, as we call RC filter circuit. So I'm going to talk about a high pass filter, I'm going to talk about low pass filter, how it works. The filters mean you design circuit that can reject or allow signals to pass. As there you have the input signal here, you make it go to the filter circuit, and you get output as you desire. First, take a look at the high pass filters. The way you connect the circuit is going to be like this one here. C in series with R, and as I mentioned before, when you want high pass filter, you see, just keep in mind that your impedance of capacitor is simply 1 over J omega C. And if you take a look at the frequency here, let's start from low to high. What is your ZL? Sorry, Z of capacitor. For low, you have a high impedance, correct? And for high frequency, you're going to have a low impedance. So for the high pass filter, you want this one to be allow the higher the higher frequency signal pass uh, and show up at the output. And if you think about a voltage divider, Vout is going to direct proportional to whatever you have here. So that's why you cannot have C down here, because with higher frequency, you take a look at this one, you have the lower impedance and your output is direct proportional to your impedance. That's why you cannot have or see here. But for the low pass filter, you definitely going to see that you probably put your capacitor down here. Okay, so just think about this one. Let's take a look at the Vout. Vout is simply apply Ohm's law. You have I multiplied by the impedance of resistor. Actually, it's become resistive. Have only the real part. Your current simply become Vin over total impedance. So it's become R plus 1 over J omega Z. And then you rearrange the term. You simply multiply, by R, the complex conjugate, of this, because you want the denominator to be the real part. So you multiply by minus 1 over J omega Z, and then you divide. Of course, you have to divide by also 1 over minus 1 of J omega C. For the denominator, you're going to end up with R squared plus 1 over omega C squared. At the top of the numerator, you're going to have this term. And finally, you get Vout to be Vin multiplied by R minus 1 over J omega Z, and then multiplied by R. Because your Vout, you simply become I multiplied by V. Or you can use like the voltage divider, just like this term here. So did I missing something here? Sorry, I have like I'm missing R here. This has become your Vout. Oh, sorry, this is, I put like the current. This is only current term. Sorry, make you confused. And Vout simply become I multiplied by R. Or you can simply use the voltage divider, right? So your Vout is become Vin multiplied by what? R, right? And then divide by Z total. That you have capacitor in series with the resistor. And now you want to find the amplitude only. You simply find Vout equal to V cap multiplied by Vout capped conjugate, and then you under the square root. So when you multiply this one, Vout and the Vout conjugate, you simply change the sign, negative side here, to be the positive side. I'll let you work out this one, right? Simply you want to you multiply the other term V cap conjugate, so it's come R plus 1 over J omega C. Okay, multiply, you're going to end up with R squared plus 1 over omega C squared. And then in you can cancel out, the top one and down here. So you end up with the square root of this term. So it's not really complicated. I'll let you work out by yourself. Now, if you take a look at the plane of your total impedance, this is your impedance plane. Just give you a better pictures. This is the real part. This is the imaginary part. So the real part you have like R, right? And imaginary part for your Z total is simply negative 1 over omega Z. That's why I have negative 1 omega Z down omega C down here. And the length of the line here, or the vector, is become the magnitude of Z total. So simply square root of R square plus 1 over omega C square. And the phase anchor simply delta Y over delta X, where your delta Y is the negative 1 omega Z and delta X is become R, or it's become the slope of the line. So you can find phi equal actually arctan negative 1 omega C over R. Okay, when you have the your V out here, I'm going to take a look at the what we call the frequency response. When you have the relation between the gain, or V out over V in, and then omega, or frequency. Okay, that's what we call the frequency response plot. As I told you, this one we work on the high frequency filter. High pass filter. So is there rejecting the lower signal, the low frequency signal, and allow the higher frequency signal pass to the output. And if you take a look at this one, you put the frequency term here. Okay, you just this equation come from the above equation. Simply represent omega by 2 pi f. Okay, and you have 2 pi f up here, and divide by 1 plus 2 pi f RC square to the power of 1 over 2. There's something interesting here. For if you were take f equal to 1 over 2 pi RC, what happened? F equal to 1 over 2 pi RC. This term simply become 1, and the denominator become 1. So you have the ratio of V out over V in become 1 over square root 2. This is we call the 3 dB point. Okay, and that's defined if you plot the gain, not just only the ratio of V out over V in, but you put like 20 log base 10, and then of the ratio of V out over V in. That's give you the gain in the unit of 3 dB, and you plug this in the ratio here, become 1 over square root 2. You're going to end up with the negative 3 dB. Okay, and that's define what we call 3 dB point. So if you put the gain here, just simply V out over V in, at the point that the ratio of V out over V in become 1 over square root 2, or your V out equal to V in divided by square root 2. That's defined the 3 dB point, or sometimes we call like the cut-in frequency. But if you were define uh, the gain in the term of dB, when you drop down or for 3 dB, it's going to give you the same point. That's we call 3 dB or point, or the cutoff frequency. And that's mean the signal that you can use for audio, or or some kind of sound or whatever, this is the range that it work is going to start from the 3 dB point. And since this one is the ratio is very low, it seems like we can reject, okay, that range of frequency. But we are going to use from the range from 3 dB to a higher frequency. Okay, sometimes we call the bandwidth. You can see your clearer picture for lower low pass filter. Okay, again, for the cutoff frequency of the high pass filter, as the circuit above, the cutoff frequency is going to be equal to 1 over 2 pi RC. Let's take a look at the circuit here. You have the capacitor 0.01 microfarad in series with 1.0 k ohms. The cutoff frequency become 15.9 kHz. And when you want the cutoff frequency to be 15.9 kHz, you know that you have only one equation, okay, but you have two unknown when you want to design the circuit. So would the R and C be? I mentioned a little bit about here. R should be much greater than 1.0 k ohms to prevent circuit loading effects. Okay, and I will explain about that later on. But at this point, just want to point out how the basic high pass filter work and how to decide. Okay, next one is the low pass filter. If you understand how high pass filter works and how to design, you do the same thing as the low pass filter. That not should be so difficult here. As I told you before, for the low pass filter, you want only the lower frequency signal pass to your output, and you don't want the high frequency signal show up at your output. So you want your frequency response to be like this one. This is the frequency and this is the gain, which can be either only the ratio of V out over V in, or in the term of dB, you simply apply 20 log of base 10 of the ratio V out over V in. You do the same thing. You want to find the cutoff frequency or the 3 dB point, so you have to derive equation for the gain or the ratio of V out over V in. And as I told you before, for the voltage divider, your V out is going to be direct proportional to the impedance at the output. And for the frequency, and this is your impedance of capacitor show up at the output. For the lower frequency, this C is very large, right? I'll put this one high, and this one is low. For the high frequency, I put the high frequency here. You know that the impedance of your capacitor simply is become 1 over j omega c. When you have higher frequency, that means this term is large, and this term drop is going to become small. Okay, so when you have higher frequency and this one is become low, so you don't need this one. You get rid of the high frequency and you let the lower frequency pass to show up at the output. So it just lets work as whatever you want for your low pass filter design. Okay, do you do the same thing? You can use the voltage divider here, quick. This one I simply put the V out equal to I multiplied by the output impedance, which at this point is become ZZ. For the voltage divider, you simply use the impedance here, 1 over j omega c, right? And you multiply by V in and you divide by Z total. It's just about math. But this one I put like calculate for the current. So the current become V in over Z total. This is my Z total, this is my V in. And you use the complex conjugate, multiply by numerator and denominator. You end up with this term. And you rearrange the term again. You have V out to be V in, multiplied by this term. Do the same thing for amplitude of V out only. So V out actually equal to square root of V cap out multiplied by V cap conjugate out. And then finally you have your V out equal to V in divided by 1 plus omega square C square R square. And when you take a look at omega equal to 2 pi f, it's become the same just like high pass filter. When your frequency become 1 over 2 pi RC, this term simply become 1. So you have the ratio of V out over V in become 1 over square root 2. And you can find 3 dB point. And that's why the ratio become V out over V in become 1 over square root 2. And you can find the frequency at this point to be 1 over 2 pi multiplied by R and multiplied by C. Or if you simply look at omega here, your omega just become 1 over RC. So that is where you have the cutoff frequency of the low pass filter. As for the phase shift, what does it mean the phase shift? When you have the input signal pass through your circuit and you have output, the phase shift is mean the phase difference between the phase of your output signal and the phase of your input signal. And you know exactly that at the cutoff frequency or at the 3 dB point, you will have the phase shift to be negative 45 degree. And you're going to have the smooth plot for the low pass filter. Okay. And the low pass filter sometimes they use for get rid of noise. But you have the high frequency noise. Okay, it's not allow the higher frequency to be amplified. Okay, or the gain is very small. That's how the low pass filter work. Okay, for this YouTube I have mentioned about more application of capacitor and inductor in the term of the filter, and I will discuss more in the next YouTube.